Okay, welcome back. This is Chapter 6. Now, Chapter 6 has got an awful lot of philosophical discussion that you may not see the relevance of immediately, but trust me, if you get a little bit deeper into it, some of this will begin to make sense. Okay, so on page 147, we're talking about formal language algorithms. So let's just talk about some terms here. A regular language, okay? That means some sort of a sequence of characters, like an English language, that can be broken up into words or tokens, okay? So if we're talking about the SQL language, well then, there's a select, and then there's a from, and those kind of things, right? If we're talking about HTML, there's a heading tag and a bold tag, right? So those are tokens. A regular expression is a technique for it's a parsing tool, that's a cool term, or being able to find those tokens. Okay, that's its goal in life, is to find these tokens that we just talked about. And so the next time, we're gonna have an entire lecture just on regular expressions, and there's a big topic. When it comes to regular expressions in Chapter 6, I'm gonna skip over it completely until we get to the next one. The next lecture is going to cover in tremendous detail, and it'll be implementation, not theory. Okay, so as an example, if I'm parsing something into words, I'm probably going to be separating on like white space, right? So a white space could be a space character, could be a new line, could be a tab. What if I had multiple spaces, right? So I'm hunting for things that exist between white space. But wait, between white space, so what if I said, Mary had a little lamb? So you can look at that and see immediately what the words are, but if I'm going to write a parser, the beginning doesn't have to have a space, does it? And the end doesn't have to have a space. So those are kind of special situations. So here I would go up to the space and stop. And so it would be Mary. What if I had a lot of spaces in here? Does that change anything? Well, no, the number of words remains the same, right? Okay? But see how this could get a little complicated, because the starting and ending scenarios may be a little different. Because I don't always start a word on a white space and end a word on a white space. Most of the time I do. When I'm in the middle, I do, but not at the ends. Okay, so in practice, a regular expression is used for something like what's called file name globbing. That's just a made-up word. But you know what we're talking about. If I do dir asterisk dot asterisk, you could say that asterisk dot asterisk is a string pattern, and the string pattern uses regular expressions to be able to find those things. Okay, that's kind of a implementation-specific example. Okay, a grammar. Almost all languages have some sort of a context. For example, I can't have in SQL, I can't have the from statement and then the select. The select has to come first, right? There's a specific order in which things happen to happen. In a computer language, it's even more clear. Like, I have to have an if statement, and then I have to have a then, and I have to have, and those things have to be in the right order, right? So the grammar is the rules, the structure that you apply to a language. So sometimes you just want to know, hey, give me the tokens. Like in this example we just did. Just give me the words, okay? I don't care what they are. Other times you want to find out, is something in the language? In other words, you gave me a word and I want to check it out to see if it exists in the language. So I run through this little routine and say, nope, that word does not exist, or yes, it does exist. And sometimes you want to see if the grammar is correct. Like, okay, is this a valid SQL statement? Is there anything missing? Are things in the right order? So sometimes it's just for tokens, find all words. Sometimes it's for something a little bit more complicated, where I need to know if it's correct. And then sometimes does this word exist? That would be the three kind of common scenarios that are used for formal language algorithms. Okay, there are other language types rather than just regular languages. There's a recursive one, a recursive enumerable, and then a context-free. Context-free means there's an awful lot of combinations that I probably can't write a rule that would make them all. Okay? That's basic. And English language fits into that. I mean, you know, Jack and Jill went up the hill, okay? Noun, verb, you know, that kind of thing. But it doesn't always have to be that way, right? I mean, Yoda would say, you know, climbed hill, Jack and Jill. You understood that, right? Just because the order was different. Okay, at the bottom of page 149, they have a sentence that has 3 words in it. Yeah, that says, non-deterministic, finite automaton. And like, wow, using those 3 words in the sentence, the very last sentence on page 147, that's a mouthful. All right, let's talk about what those things mean. Non-deterministic. Non-deterministic means there may be more than one answer. In other words, if you ask for something, it could be, well, maybe the answer is 12, maybe the answer is 42. That is one use of the word. Now, later on, we're going to talk about non-deterministic probability time. All right? And in that particular scenario, the word non-deterministic means I don't know how long it's going to take. Okay, that's what the word means. So non-deterministic basically means I don't know. That's what that generally means. In this case, what it means is I'm not sure what I can get you an answer, but it may not be the same answer for every single input. I might give you something slightly different. So non-deterministic. Finite means there's one and only one answer. Cool, that makes sense. And an automaton is a type of thing that we're going to build. We're actually going to build us an automaton. And these things, they have horrible names. They're called abstract machines. Just bear with me. This one's tough to swallow, so just hang on. All right. So yes, we are going to get to all 3 of those words. Non-deterministic, finite, automaton. So on page 149, they start talking about the formal language basics, which is, of course, like this stuff. Okay, so if I have a language, and they use so an alphabet is, you know, a language is made up of an alphabet plus some grammar, but hang on. So let's say our alphabet only had three letters in it, A, B, and C, and that's it. So I'm using little sigma symbol over again. You know, before sigma meant like summation, the Greek letter S, but that's not what it means here. That just means this is the alphabet. Okay? So that means a word could be made up of any one of those things, any combination or duplicates. So as long as it has an A, B, or a C, it could be A, or A, B, 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 B. All these things are all different words based upon that alphabet. But you can also have a word that has no symbols in it, basically nothing, like white space kind of a thing. And it's called lambda. It's for an empty word. So our alphabet could be made up of that or nothing. Cool? All right. So alphabet symbols. And then there's some operators. So the first operator we look at is the little style character on both sides. This kind of sort of is the same symbol that we've been using for doing floor, but that's not what it means here. What this means is the count of the number of symbols in the alphabet. So in our case, this would be 3. Cool? All right. So, concatenation. Ooh, that's a cool term. Concatenation basically means join together. Okay, it's just a fancy term for joining things together. So if I had a word X, and a word Y, and I want to combine them together, I would just say, X and Y. So if this case W is equal to that, and X is equal to that, well then WX is just taking those 2 pieces and cram them together. That's not complicated, is it? Okay, good. And then you might want to have something that does a reverse. So that's a subscript with a capital R. And that just takes the letters and boop, turns them around. That, again, not too complicated. And then you could have repeated concatenation. Go concatenate yourself. Sounds like a curse word, doesn't it? But in this case, if Y is equal to AB, then Y cubed would be AB, AB, AB. Okay? So if you're scratching your head looking at this going, okay, what's this all about? Just hang in there. Hang in there. I promise you, it'll make a little bit more sense. The next thing to talk about is closures. That's a weird term, and we are definitely gonna hit closures when we talk about the practical implementation of regular expressions in the next lecture. But right now, what closures? There's a star closure and a plus closure. Star closure means I can take, like I'm concatenating words. I'll take a list of concatenations of the word or no concatenations. In other words, kind of sort of like this example here. If I said dir, let's do junk dot asterisk. Okay? So in their world, asterisk means I can match anything or nothing, which means if I had a file that did not have a file extension, it would match. Cool? The plus sign is very similar. I mean, this is not valid DOS command, so just bear with me for a minute. So the first one, if I had a regular expression thing that did that, would mean it would match junk plus anything else that had started with junk. Or if nothing. So asterisk means all or nothing. Plus means I'll take all, but I will not take nothing. In other words, you have to have something after that. So that's the difference between asterisk and plus. And to tell you the truth, you don't have to worry about it in this chapter. But the next lecture, we're gonna hammer that one big deal. Anyway, it's called closures. Okay, so the definition of a formal language basically means I have all the words and there's no repeats. Okay. And there's a lexical ordering. Ooh, lexical ordering. So here's an example of lexical ordering. So let's just assume that there's a maximum word length of 3, okay? And here's my, so I would start with nothing, and then A, and then B, and then AA, and then AAA, and then it would just repeat, right? Over and over and over and over and over. So this is the proper lexical ordering of this particular language, whatever this language is. And you might look at that and go, well, wait a minute, that doesn't make any sense. But wait, remember we talked about how the SQL statement, for example, has like a select and an asterisk from and the table name, right? Well, that could have nested things, right? So instead of having a table could like be another select statement. So it'd be select asterisk from table and then select. That's what we're talking about. When you have two A's together, it'll allow you to process the A and then turn right around and process the A a second time. So this type of thing is really talking about recursion, okay? It's not immediately clear by looking at their example or reading the text, but yes, that's exactly what they're talking about. They're talking about the ability to handle nested things. Okay, on page 152, they start talking about this thing called an abstract machine. Now, this is going to bend your brain for just a minute, so just bear with me. Okay, an abstract machine, well, first of all, what does the word abstract mean? Abstract means it ain't real, okay? Abstract means this is a thought experiment. So these abstract machines that are describing in the book are not real things. You don't physically build an abstract machine. It's just a thought experiment. So these things are completely hypothetical, okay? Good. So they're rule-based. They're based upon this goofy thing where you have some sort of an input, and the way they describe it, it's a paper tape that contains symbols on the paper tape. And then, so that's my input. I have some sort of output, and it can remember what state it's in, whether it's processing a word, like if it's in the middle of a word, or if is it processing white space, for example. So it's about input, output, and maintaining state. That's basically this whole thought experiment. And we're coming up on the 15-minute mark.